Hello and welcome back. Today we want to talk about data-driven modeling and in particular how to use physics-informed neural networks. So machine learning is generally about big data. That means the typical machine learning approaches that we train with lots and lots of data. The more data we have, the better. And what we typically do in machine learning is that the machine learning learns essentially the mapping of the data, like the feature variables x, towards the target y or our label y. So this implies that we don't model the system explicitly, we learn everything from the data. This is, in general, the core idea of machine learning. We do need to make a few assumptions when we do learn from data. So first of all, that we have enough data that we can learn from, and also that the data that we have represent the system rather well that we want to learn from. Otherwise, the machine learning model will learn something, but not what it should learn. We also, of course, need to assume that the data are correct. If we have wrong or low quality data, then we cannot hope the machine learning model to extract any useful information from them. And we also need to assume that all relevant aspects are represented in the data. That sounds more trivial than it is, because maybe we have rare events or a number of occasions that don't happen very frequently. We need to be able to include those in the data as well. However, in many systems, or in modeling many systems, especially in engineering and physics and so on, we know a lot about the systems that we do want to model. So we, for example, know the general behavior or specific properties of our system, or how it reacts if we give some sort of input into the system, like an external stimulus. In many cases, we can mathematically represent this as differential equations plus boundary conditions. So how can we solve those in general? For some of those there is an analytic solution. This is the best case, because then we have an exact solution that we can work with. There are also a number of transformation approaches like Laplace, Fourier or wavelet transformations that help make the differential equation easier to solve. Sometimes it's also enough to approximate the system that we have a differential equation for with a simpler system. That is good enough, shall we say. It's not exactly the system that we want to model, but all relevant aspects are covered to the degree of accuracy that we require. And then this model system can then be solved better, easier, with the methods that we have. There are also a number of numerical methods like optimization techniques, finite element simulation, finite differences, and so on. These are all very well, but they are very compute intensive, especially if you require a high accuracy. The same is true for probabilistic modeling in terms of probability functions. We can reformulate many systems as a stochastic process and solve these in Monte Carlo approaches, but again, this is very compute intensive. All of these approaches in common have that we have a known system, but very sparse or very little data. So how can we now use neural networks in machine learning with sparse data? So essentially we want to generalize the machine learning models that are commonly used to the extent that they can make correct predictions outside the training data regime and work with sparse data. In practice, this is quite difficult because, as we said before, you need typically lots of data, and then only then the generalization ability of neural networks is okay-ish just outside the space that we represent by data, but not much more. Let's discuss a simple example to illustrate how we can work with these kind of things. So let's say we have a body like a hot metal rod that cools off in a large reservoir, for example, a large water bath, and we assume that the large water bath is large enough that the temperature of the water doesn't change and so on, so we avoid any complications from realism that we can need to include in a realistic system. So the differential equation for this simple system is also quite simple, obviously, because the temperature change with time depends on the temperature of a reservoir, some critical time scale that essentially determines the cooling rate and the current temperature. So you can see the differential equation here. We can solve that, of course, analytically. It's a rather simple differential equation, and you probably all know how to do that in a heartbeat. So here is the exact solution, and of course for such a simple system like our coffee cup cooling on the desk in the surrounding air, this is simple enough to model. However, in many cases we only know the differential equation and not the exact solution, and this is why we're trying to find methods that are both compute efficient and also work with sparse data. We could of course just use neural networks as we have encountered them so far. And we have now, let's say, 10 training points. And as we know, the differential equation is very simple, so we might hope that the neural network would pick it up. It's only one parameter in the end, the cooling rate. So let's see what happens if we have a simple neural network trained on those 10 data points. And if we do that, we can see it's sort of okay-ish, apart from this big dip in the first region around the first 2 data points. And then it sort of learns in the correct behavior inside the regime of the training data, but as soon as we leave the regime, the solution diverges strongly from the expected known analytical solution. And why is that? Well, the neural network has picked up on the data points, but it hasn't actually learned the physics of it all. It hasn't learned the differential equation, and it hasn't learned the time constant. So this is the idea behind physics-informed neural networks. So we use the neural networks to solve the differential equation numerically, given the sparse data that we have, but we extend the loss function such that this captures the physics of the term I, the differential equation that we have. So the total loss is the data loss. This is, for example, our 10 data points, because we essentially need the data to represent our boundary conditions, plus some contribution that accounts for the differential equation. So this is how it looks like for the data loss. We take the, for example, for our regression problem here in the case of the cooling rod, the mean squared error, as we typically do, and then we have our physics loss. And now this looks a bit different because we have these, as they're called, collocation points, TI. They enforce the structure of the differential equation of the neural network, and they are not limited to the regime of the training data. They are really representing the differential equation where it should be valid. Right. So the key idea is, again, to add the contribution based on the derivative of a neural network with respect to the input space. Right? So this is how we encode the differential equation and compare this with the differential equation of the system. Right? So we use the differential equation and see how the neural network would compare to this. How do we do this is actually a neat trick, because these modern deep learning frameworks, what they really are good for is not only matrix multiplication, which we need in backpropagation, but also the automatic differentiation, which we also need for the chain rule and the backpropagation algorithm, if you remember. Right, so we exploit this so we can take the derivative of the whole network and compare this to the non-differential equation. Let's take a simple example. Let's say we want to learn f of x as sine of x with a known derivative cos. Right, so this is very, very simple, and we know the analytical solution, so we also know what to expect and what to compare to. So we make a first plot, right? So we have our lint space for 2 pi, and then our data is just the sine function of it, and then we have a model, right? So we can train that and make our predictions, right? And then we have the usual data loss, right? We have our predictions and the training data in the regime. And then we have the differential part, dy train. So this is where then the auto differentiation comes in. And we we differentiate with respect to the input space. That means we want to differentiate the neural network with respect to the X-trained data samples that we have. Right? And then we have in the next part the physics system, the physics loss. And here we take the absolute value between what we want to achieve, because we know the differential equation is the cost function, right? This is what you see down here. And dy train is now the derivative of the network. And this should be small. That means we enforce that the network obeys the differential equations. And then the total loss is the data loss with the points that we have plus the physics loss. And then if we do that, we can see that indeed the prediction is the derivative. Now let's do this for our example for the cooling steerod or our coffee cup on the table, right? We have the differential equation here just to remind you, and if we now encode this differential equation and use the autogradability of the PyTorch framework, you can see the blue line is much closer to the theoretic curve. The BIP at the first 2 points is still there, but much less pronounced. And if you go outside the data points in red, you see that the neural network has now picked up on the physics information. Now, let's play devil's advocate. Isn't that like cheating? Don't we put the known solution in? Well, no. Because we know something about the system, or we have a hypothesis that we want to test and so on, we know we want to look for a solution. It is a bit different from our traditional use of neural networks and machine learning, but is much more aligned with how we approach a numerical solution of solving a differential equation. There we also have the differential equation and a numerical solution, and we also have a few data points given the boundary conditions. So we're not aiming here for the network to learn the underlying physics from the data points that we have, but we say we have the data points representing our boundary conditions, and we know, or we assume or suspect or have a hypothesis for the physics of the system given by the differential equation. So the key points here are many systems in science and engineering can be described by partial differential equations, but only few of them can be solved analytically. Right? So we typically have to resolve on numerical methods and approximations, and physics-informed neural networks are able to incorporate information from the differential equations and the measured values or boundary conditions or initial values, whatever you have specific to your system, and then integrate that into the loss function. And the key idea behind doing that is to introduce this physics-based loss and differential neural network with respect to the input space, for example time and so on, and compare that to the differential equation.